and the tech has been thoroughly integrated. So okay, I cannot see the slides, all right. Okay, so this is a design pattern that says that streaming or event-based processing in the future will be more heavily integrated with machine learning. But let me start with stream processing. So I told you before, for those who were here, and those who are not here now, that streaming considers data as in a very natural way. So as a continuous resource, things are happening and generating data, and we can actually, when we are talking about streaming compute, we can actually generate knowledge as the data is being ingested. And I'm sure many of you are familiar with this concept already, because there was a paradigm shift that happened a few years ago. If you're not familiar, I will tell you briefly the story. So after the peak of large-scale processing and MapReduce and Hadoop and Spark, a new generation of systems came into popularity, let's say. And that was a kind of systems that was doing really large-scale processing, but with unprecedented low latency. So really fast and large data. And the paradigm shift that they imposed was that we no longer consider the data as, this static box here, where we actually send queries or do analysis, but we actually submit our logic into the system, and we let the data pass through, and using data flow operations, create useful state that we can use for analysis any point in time. Then it's always in sync with the current data. And there's an actual stack. I'm sure you have already used at least one of these systems, starting from the storage level. There's Kafka, that is a partition log. There is PubSub from Google, Kinesis, Pravega. Primarily in the compute, there's a lot of things going on. So systems like Flink, Beam, Apex, and so on. What they're doing is that they allow you to program in different programming levels of abstraction, your continuous processing logic, and accumulate state, run aggregations, and produce some live real-time knowledge. At the high level, what is interesting nowadays is that there are a lot of standards being developed. For example, in the relational data processing, there's a calcite SQL standard for evolving SQL for real-time data, for streaming data. So if you haven't checked calcite, it's already running in the world's most popular stream processors. So Flink and Beam, for example, support calcite SQL queries. Oh yeah, it's the other one. And for those that are really into engineering, this idea doesn't sound so new, because probably you have implemented some real, live services. And those services are typically implemented using actor programming frameworks, for example, like Akka. And they actually get real-time events from the user devices, from the web, do some processing, probably communicating with a database from doing transactions with user data or orders, things like that, and going on 24/7. But there are a few key differences here. The actor programming and microservice technology is operating at a different level. So first, we have a low-level event-based programming when we're talking about actors, while streaming allows you to declare your logic in a very abstract level. So fewer lines of code, more simple programming languages to use. And then we have the notion of state. When we're programming with actors, state has to be managed by the user in most cases. So you usually keep your state in a database, and your actor framework is communicating with the database, for example, or a file system, while in stream processing, the state is something internal in the stream processor. So you don't need to care about how to declare your state, how to synchronize it, how to do fault tolerance, which is very important. That was one of the holy grails of data stream processing for many years. And finally, scalability is automatically done when you're working with data streaming systems. A few words about Flink. Why Flink? I worked on Flink in the early days. When I started my PhD, I was one of the early committers of the system. And it was basically a collaboration between Sweden, KTH, and Germany, TU Berlin. Later on, of course, as you probably know, Flink became really popular. It's the #1 stream processor nowadays. It's being used a lot for real-time analytics. There are more than 400 open source contributors and hundreds of deployments. And all of these companies are using Flink basically not just for exploratory data analysis, but for running critical services. And of course, Flink has also influenced other systems that you might be familiar with, like Spark, the call-side SQL, Storm, and so on. So where is streaming placed in the end-to-end data processing pipeline? It's doing the computational load, right? So you have your devices generating data. Your data might go into some file systems, some event logs, data lakes, whatever you want to call it. But it's being ingested as a stream, no matter what's the intermediate storage type, and accumulating state while this thing is running. There are many tasks deployed when you're working with streams, so it's a distributed way of running applications. And of course, the end results are the state that you can probably query and the output. People use Flink today and other similar streaming frameworks because and primarily Flink, because it provides a lot of automations in different types of programming levels. So starting with the Dataflow Engine, this is a distributed system that is purely automated. You don't need to configure it. It runs your logic and partitions the state, and provides automatic fault tolerance, so you don't need to worry about machines failing. It scales out when there's a lot of data, and it also provides the user with useful insights and analytics while the job is running. When it comes to programming APIs, there is support for low-level APIs, where users that previously run and declared logic in actor frameworks are familiar with. Now they can run similar applications and declare them using a low-level event processing API on Flink. The difference here is that the program state is something explicit to the system, and there's also this notion of out-of-orderness. I don't know if you've heard, but if I can explain it in one sentence, is the idea of giving the programmers or the data analysts the impression of linear time progression, even though events might arrive in different order. So if one device has a clock skew with another device that's generating data, it doesn't really matter, because the stream processor can wait the right time that is needed to offer a linear progression of time for your computation. And then we have the core API, the data stream API, which is functional programming. So you define your logic in harder functions. There are windows that you can group data based on their timestamps. And domain-specific APIs, as I mentioned before, doing SQL and things like that. Here's how a declarative query looks like. This is receiving two types of streams, a write stream and a fair stream. It looks like a classical SQL query. We haven't put anything extra here. And of course, what it does is that it correlates those two streams by some ID, and then checks for tips. So tips usually happen in the last 5 minutes of a taxi drive. So these are things that are happening in real time. There's a start event and an end event. We don't have time to explain this in detail, but the key points here is that we can group these events, correlate streams, group events by some time characteristic, like group them by hour, and then produce some live aggregates while the events are being ingested. Another example that is really typical to telecom users, for example, is complex event processing. And that's a simple idea of declaring your logic in a sense of a pattern, a sequence of events that might happen in your stream. And of course, taking those patterns and doing extra computation on top of these patterns. So here, for example, we are having two patterns. One is for the completed writes, so an event, a start event followed by an end event. And then we have a pattern that is actually filtering out all the completed writes within 120 minutes. So these are really simple examples. Here's a case study, if you're in the business level. What systems like Flink have changed in the landscape of data processing. Well, there has been a paradigm shift in the way we do dynamic pricing, for example, especially in car sharing. So Uber was one of the early adopters of stream processing, and Flink, more specifically. And they started with a very lightweight and more less critical application that is Uber Eats. So what they want to do is to provide a way for the user to get a good estimation of the delivery of the food, because if they're hungry, they need to know when to expect their food. And then the restaurants wanted some insights about their hourly earnings, daily earnings, and knowledge that is really useful on the spot. The way they did it is by writing a simple Flink pipeline, basically, that was running in their backend. It was receiving all of the requests from the users, the orders, the availability of the restaurants, and producing some simple aggregates. Nothing really fancy here. It's not machine learning, I would say. But still, they provided a SQL interface to query that state and provide these insights to the users and the restaurants. But since that was successful, they moved ahead and ported this technology into a very critical part of the business, and that was dynamic pricing. So dynamic pricing is what defines the competition, right? It's what gives a good deal to the user and also a good profit to the taxi driver. And of course, there are many correlated streams here. We have the supply stream, demand stream, and everything is correlated by the geographic location, so there are many parameters here. So what they did is that they split their logic into an offline pipeline. That was a TensorFlow-heavy job that was producing like a model. And then they had the serving side and a real-time aggregation side that was running on Flink. So this way, they could periodically, like once a day or every few hours, get a live model, parameterize it with the aggregates from TensorFlow, parameterize with the aggregates that get produced from Flink, and give this and provide the right price at the right moment, let's say, and in the right location. And if you've been to the US, you might have seen that there are many dual company drivers. So people like to taxi drivers like to have multiple of these subscriptions to Uber, Lyft, and so on, and always pick the best deal, right? What they can make more profit. And pick customers from both. So Lyft had to join the competition because now Uber was doing dynamic pricing. So next year, at Flink Forward, a conference on Flink, Lyft presented their own pipeline that they use for dynamic pricing. That was, again, based on Flink, this time primarily like only using Flink. So it was really adapting faster to changes in different geographical cells. And they also used that not just for defining prices, but also as a way to doing load balancing of the taxi rides, so that they can really match the demand in each area, and also don't get too many taxis in one area that doesn't have so many customers. So Flink is cool, and in general, stream processing has a lot of benefits. I was really proud when I finished my thesis that I've done like a big step for humanity. By work on fault tolerance and very critical things in this type of tech. But of course, as everybody that does a PhD, after a few months maybe, or a few days, you realize maybe there's a lot more. you exit your cave, and you see there's a lot of more things happening. And that's where I discovered machine learning, let's say, in more detail. And I realized people are doing a lot of more things and more complicated things. And the other systems, like TensorFlow, maybe they are doing something really that stream processors cannot do, right? And that was true, actually. Systems like TensorFlow do iterative-heavy computation, and they are really specialized for what they do. And of course, other systems like batch processors, Spark, are specialized for specific frontends, like DataFrames. If you want to use DataFrames, you either use Pandas, let's say, or Spark if you want to scale out. So the big picture was really scary. I mean, there are so many things, so many especially where that involves one big end-to-end pipeline, there are many components that run in different systems. And that's because users prefer different front ends, right? You might prefer to work with streams if you're a data engineer, for example. But if you're a data analyst, you want to run your tasks of the pipeline and write them in Python, let's say, and run them on TensorFlow. So that's a very tricky thing, and especially if we look at the heart of the problem. Pipelines are composed by different systems, right? So at first hand, we have these silos, right? So we have experts in one system, experts in the other. That fragments the code base, first of all. Then what we have as a problem is that hardware is unshared, right? Because we have to dedicate containers for this thing, runs on GPUs, dedicate containers for a Flink job, runs on CPUs. And really, frameworks also specialize in different hardware, right? We know that if we want GPUs, we run TensorFlow. So that is really problematic because at the end, what we end up doing is that we have a pipeline, but it's really decoupled. And then we end up serializing data, converting data types, sending them over the network, storing them in some disk, deserializing them. And there's a lot of heavy I/O because in both ends, right? Because let's say I use a stream processor or a Dataflow Engine to do the pre-processing, data cleaning, data integration, things that can be done on the fly. And then we use the heavy workload machines like ML frameworks to create a model periodically. And then we have to also transfer this model to serving side. So this leads to ridiculously unoptimized programs and pipelines. And of course, we cannot have what I explained before, this continuous intelligence, really, because of this decoupling. So what is the next paradigm shift? So our job is to think a bit ahead, like 5 years, 10 years in the future. Even though we are a systems hands-on group, we try to prototype things that might be useful in 5 years from now. So what is really the next paradigm shift? We were thinking a lot. And this is a question I pose to you. We found some way, but I don't know if you can find it. It's a revolutionary technology that does not require you to throw tons of data to your problem to solve it. If you're into ML, there's no answer. Maybe reinforcement learning, I don't know. But this is not the answer. The proper answer is the compiler. Because if you think about compilers from your studies, compilers can understand instructions, really high-level instructions declared by humans, and then optimize them and translate them for primitive machines to understand, small like assembly instructions. So given that notion, a strong notion of the compiler, we designed a new architecture. We call this Archon. And the idea is that at the top level, we want to offer a unified data analytics declarative programming DSL. And that DSL, we want to provide first citizen support for some core data types. And those are relational, tensors, linear algebra, and streams, the 3 core data types. I have also graphs here, but we're still skeptical about graphs. We might want to implement them on top, but the first 3 are the core data types we want support. And then at the other end, we want to produce generate code that is targeting any hardware that you have available. You might have FPGAs, you might have GPUs, or simple commodity hardware. We want to optimize the code, high-level code, and generate optimized machine code for those devices. And also scale out, of course, big data. This is how our stack looks like. Of course, this is a prototype research project. You can still use it already. Some parts are already not production ready, but they can run, they can compile. So we have the unified analytics DSL. We have the core of the whole idea, which is an intermediate representation that I will briefly talk about, and also a runtime that can execute your logic in different hardware. About the DSL, as I said before, we want these core data types, streams, linear algebra, and relational algebra, but we also want to offer different embeddings for the right language that you want. So people are more familiar with Python. We won't support Python. It doesn't really matter. What we're thinking of is to be able to intermix across languages as well. So one part can be written in Python, another part, let's say, in Scala. Because you have to combine the work of engineers and data analysts. And how do we do that? It's actually a tricky thing, right? Because you have different languages, you have different types of the language types, and of course, you end up again into the same situation where you have to convert types, serialize them, pass them into the next function, and so on. So this is not really a good idea. And of course, it leads to performance degrades. The more complex your pipeline is, the more frameworks you're using or languages, the more the overhead for context switching here. So instead, what we want is a linear, like a constant performance that is not really affected by the complexity of the software that you have. So that's where the IR comes into place. So we want to be able to translate every type of function into the same representation, and then be able to fuse and do all sorts of optimizations and cross-compilation of that logic. This is how our compiler pipeline looks like right now today. So we have, we start from the language-specific parts, and we keep optimizing, doing logical optimizations, physical, and then producing binaries. We have a paper on the intermediate representation. We don't have time to explain this today, but the idea is simple. It supports, it's a minimal yet feature complete set for read-only types and expressions, and it can support all existing like batch operations known, and all streaming operations. That includes windows, streaming maps and flat maps and reduces and every sort of known function. So the compiler can do crazy things that we know from the past as well. So loop unrolling, partial evaluation, vectorization, if the CPU supports it, and also data flow optimizations across languages. This is an example of how our IR can even speed up existing frameworks, not just our framework. So we used the principles from our IR to prove that the amount of speed up it can offer a priori on a large Flink application. Flink, of course, as you know, is written in Java, but of course we can take Java, convert to IR, and then generate Java again. And of course, and when we do that and apply all of these optimizations at the instruction level, we can end up with almost 2 orders of magnitude faster execution. This is a very recent research paper that was published in accepted at SOC this year, and it shows the progression, the evolution of data processing frameworks. So at one end, you see we started with either batch or streaming frameworks like Hadoop and Storm. Then we had 4 years of pseudo-hybrid systems. Like Spark was claiming that they can do streaming, but instead they were doing streaming, emulating streaming on batch. It wasn't really effective. And of course, with Flink, we claimed that we can do batch, but it wasn't as good as the dynamic task scheduling of Spark, for example. So now we enter an era of hybrid execution systems, and that's where our runtime goes into, it can be mapped to. There are other existing systems, also researched, like Ray from Berkeley, but we believe that Archon has the right execution abstractions to support and optimize any type of computation, since we can have the traditional data flow execution with static tasks, but also dynamic task scheduling for large batch jobs. And of course, we write this in Rust because we want to have good performance. And it's also a fun language to learn. I want to finish with this slide. So our Arc optimizer can offer a priori 10x speed up, roughly. Shared hardware acceleration can offer you 100 times speed up, especially when we are talking about GPUs and FPGAs and specific operators, of course. And then when we are talking about data parallel execution, we can run this logic in thousands of machines. So we can scale up to thousands of times. These are the takeaways. This is our vision, and that's what we want to implement with the system, while also allowing interoperability and a unified way to declare analytics and execute them. You can read more about the project here. So we have a website. It's a little bit outdated, since we are mainly working on the code. But you can also check out all the sub-projects involved in this system. Thanks a lot.